Well, hello everybody. In this module, we are going to continue on, and again, we're focusing on why our sublevels split, and we are going to go over the three concepts, and we're going to begin with Coulomb's law. Now, Coulomb's law, here's the formula, and we're not going to use this formula. We're not going to do calculations with it. I'm just going to go ahead and introduce it to you and go ahead and give you some conceptual information from it. Now, we talk about potential energy. So our potential energy is going to be due to the attractions and repulsions between charged particles. See that N right there. Now this E right here, that is our potential energy. 1 over, or I should just say that this is a numerical value, so 1 over 4 pi epsilon naught. And then this Q1, Q2, those are your charges of your particles. And here we have our R. Now, our potential energy is inversely proportional to R. Now, R is the separation between our charged particles. And if you recall, systems tend to go toward a lower potential energy to be stable. So, systems tend toward lower potential energy, and this leads to stability. So we're going to have two instances that we're going to look at right now. We're going to have similar charges. So if you have similar charges, the potential energy is going to be positive, and this decreases as the particles get farther apart. Okay. And that means our R is going to have to get larger. So like charges are going to repel each other. So as those like charges get closer together, you have an unstable system. Okay, so that's not very stable. So higher potential energy, not very stable. Now, if you have opposite charges, the potential energy is negative. It's negative. And becomes more negative as the particles get closer together. So this is when our R, looks like a V, but that's an R, is getting smaller, R decreases. So those are becoming more stable as they get close to each other. And that should make sense. You guys have already learned that opposite charges attract one another. Okay, so that situation is more stable. Now here, we can talk about the magnitude of our interaction between charged particles. This increases as the charges of the particles increases. So here, if we have a nucleus, say that has a +2 charge, and say we have over here a little -1 charge. Well, what's going to happen is that, well, let's contrast it with something else first. So then we have a +1 charge in the nucleus. So let's just say that's the nucleus. This is the nucleus. And then over here, we have our same -1. Well, here, our magnitude is higher here. So it's going to be more strongly attracted to that 2+, or the +2. Okay. So that's between the electrons and nucleus of the atom. So I was just talking about that. So the greater the attraction, the more stable the electron is. Okay. So again, electrons are attracted to the nucleus. It's positively charged, and hopefully you guys recall it's called an electrostatic attraction. Now, electrons in orbitals closer to the nucleus are more stable. So n = 1 would be more stable than an n = 4. Now, for different sublevels, and if you're in the same principal energy level, and so here I have an example with 4, so it would be n = 4 here. N = 4. Some orbitals have a low or a lower energy, and they're more stable than the others because of shielding and penetration. So our 4s would be more stable than our 4f. Okay, so let's talk about shielding then, because we just talked about shielding a little bit ago. Now, what is shielding? Well, if you have more than one electron, electrons can experience an attraction to the nucleus, while also repulsion with the other electrons near it. Okay, so repulsion to the other electrons. Now, the amount of attraction that an electron can feel, I went over it in the beginning, but it's called the effective nuclear charge, and there's actually a formula for this. So Z effective equals Z minus S. Z is the number of protons. S are what we call your shielding, or the core electrons. Okay, so let's look at an example with this. Okay, so I have an atom here. So this is lithium. This atom is lithium. And what I want to point out first is we talked about what electrons experience, and you have an attraction to the nucleus. But here I want to go over these inside. These are our core electrons. And what happens is that we have some repulsion. And each of these, in our core, each electron feels a full +3 charge. So there are core electrons, there's the nucleus, they're attracted to this nucleus, but these electrons here in the core can feel the whole 3+. But out here by its lonely, we've got a valence electron. Now, this valence electron, due to these electrons in the core, they don't get to feel this whole +3 charge. So due to the core electrons and they're being repelled, they are blocking the full charge. So this only feels part of the charge. This feels part of the charge. Well, how much does it feel? Okay, so we have that formula, Z effective equals Z minus S. And we know Z was the number of protons. So this equals 3. And then how many do we have in the core? We've got 1, 2. So 3 minus 2. So it has they can feel a +1. So this electron only feels about a +1 charge. So if it feels only +1 of a charge, that's still this electron, we have weaker electrostatic attraction. And if it has a weaker electrostatic attraction, we can remove that electron easier than a core electron. So that's why with these valence electrons, when they're removed pretty easily, right? So we learned that in intro. So what happens is that you just have that weaker electrostatic attraction. Okay, so remove it a lot easier. So electrons that are farther away from the nucleus, they have a lower effective nuclear charge. This makes them less stable. And then they also have a higher energy. Okay. So also, let's talk about orbitals a little bit. Electrons in s orbitals. Electrons in s orbitals, well, we know that they're spherical, and they are actually better at shielding or blocking the positive charge of the nucleus. So they do this better than our P and the D, and that's because of their shape, because of that spherical shape. Okay, so I'm going to finish this module, and then we're going to go on to penetration for the third concept of why our sublevels are not degenerate.